So let's start with the central part of this article, which is recursive reasoning networks. And let's move towards what the problem statement actually is that the authors want to solve. So first of all, the language that they consider is a subset of Datalog. Datalog is a very classical language at this point, where it's very, very closely tied to the databases community. And in the subset that the authors use in this paper, the relations have variety 1 or 2, like I mentioned before. We have no functional symbols, and we have rules with the symbol bottom or contradiction in the head that are allowed, and these rules represent constraints. So bodies that lead to something that can't happen. Rules are of the form, you have a conjunction in the body leading to an atom in the head. Negative constraints, like I just said, are bodies leading to a contradiction. And in both these cases, alpha and the betas are atoms, and n can be 0 or greater. So facts are just ruled without bodies. So we could have alpha where n equals 0 here. Would be a special kind of rule. Literals, as usual, are either facts like alpha or a negated fact like not alpha. And databases are just finite sets of facts. Here's another kind of example, but in this case in the Datalog language. So very similar to what I was saying before, adding the constraints that I didn't have, where we have things like if X is holding something, then X is human, or as it says here, only humans can hold things. And only objects can be held. So if 2 elements are in a relation, here we use the underscore for an anonymous variable. We don't need to refer to it, but it could say here X as well. Then Y is an object. These classes are disjoint, so humans and objects can't have no overlap. That kind of thing. Here we have a little bit of an example of reasoning like before. Objects are at the same location as the one holding them. So if X is holding Y, then Y is at the same location as X. And then we have a few facts like Mary is holding an apple and Mary is in detention. Then queries that we can ask is very similar to my example with Michelangelo. We can ask, is the apple a human being? This evaluates to false. Is the apple in the kitchen? That kind of thing, right? Just using simply these rules and the facts. The language semantics is straightforward. I won't dedicate much time to this. It's defined as usual with urban interpretations, satisfaction of rules by these interpretations, logical entailment of facts by sets of rules. So we're trying to encode what is meant by truth in this language, basically, right? There's an interesting aspect here. So they use the closed world assumption. So negated facts can be derived using the closed world assumption. They also have this local variant where they consider this this notion of atoms being close to each other. But for those of you who haven't heard of the closed world assumption, it's simply saying that if I cannot model a fact, then I will say that I will conclude its negation. So if I don't know about something, if I can't prove something, then I will prove that its negation holds. And the logical entailment is denoted with this usually use the turnstile symbol where this is like a bar instead of a tilde, but in this case to make sure that we're using this kind of the author's notion of entailment, we use this symbol like they do in the paper. Further, they assume that like I was saying before, that the database is variable and of size k. We'll see why we need to specify the size. Sigma, which is the set of rules, is fixed, and the literal L will also be variable. We'll use that as the query, right, to make predictions. So then the problem, we finally reached the problem. So given a database D, a program or set of rules sigma on the literal L, decide whether the database and along with the set of rules derives or entails the literal in question. So the solution, the goal that we have in order to solve this problem is then in the context of this article is to derive a neural network that will be denoted with n sigma k with a binary output that then, given some sort of encoding of an arbitrary database of that size at most k and an arbitrary literal, then we can have this characteristic function where we have the output being 1 if and only if this holds true. And what the authors do is to craft these recursive reasoning networks that are designed specifically for this class of problems. We'll see that recursive or RRNs are a special class of recurrent neural networks, the recursive neural networks. So a few intuitions then. The idea is to replace, sorry, is there a question?
So on that previous slide, so the database of facts isn't passed to the neural network, only K, only the size of the database?
No, it says given an arbitrary database D of size at most K. You have to have the facts.
Okay, yeah, I was just confused from like the N of sigma K, but like the
database.
Here,
yeah. Well, actually, wait, no, you're right. The neural network, we'll see this in a bit, it won't get the rules either. It will encode the rules, it will learn the rules and the embeddings of the individuals, and then given the literal, will tell you if it's entailed or not. So it is taking the database in the sense that it's encoded already inside as embeddings. Maybe it'll become clear, hopefully, a little bit
the
later.
Difference, Jerry, that they use the database to create training samples and the rules to somehow extract the structure of the embedding.
Right. So the database, right, it's used to, as we'll see in a bit, is used to learn the rules. Actually, it's the only thing that they use the data for. Yeah, that's right. Okay, hopefully it'll become clear in a bit. We have graphs and everything. So the idea is then to replace formal ontological reasoning with computing a deep neural network called an RRN that is trained relative to a particular ontology. So it will be independent of specific facts, and the vocabulary of classes and relations will determine the structure of the layers in the RRN, as we'll see. And as I was just mentioning, the rules are not provided, so they must be learned from the training data. And so that's why I guess in the notation we have n sigma, because the sigma are being learned, the rules are being learned. And the application of the trained model on specific facts will be done in two parts, two stages. First, we generate vector representations or embeddings as usual for individuals in the data, and then compute the predictions for queries based only on these embeddings. So learn a little bit of intuition on what the learning will be. So based on typically on the same idea as typically machine learning approaches are, that all information on individuals that are in this case both specified or inferable can be encoded in embeddings. And the process starts, the learning process starts by, like Paula was just mentioning, randomly generating initial embeddings for all individuals and then iterating over the data, updating based on training data to update the embeddings of the individuals involved. And this considers not just the provided facts, but also the possible inferences that can be made via the rules. So this clearly will involve going through all of the data, the training data, multiple times. But as the authors point out, it's essential. It's impossible not to do this because we want to encode reasoning chains. This will come up in the empirical evaluation explicitly, because we'll see what happens when we allow for less layers in the model and try and learn anyway. So the process itself, like I mentioned before, is the same as that for learning classical RNNs. It's just a way of the clever aspect of the paper is how the authors craft the layers so that everything works out. So this is the graph that I was promising. So we go through the data, we separate subject, predicate, object, and as we'll see, we'll have an aspect, a part of the model that will look at, it'll look up the embeddings in both cases, right? And then update the model. So for prediction, the intuition is that the learned embeddings can then be used to answer atomic queries. So this is one of can be seen as a limitation of the model, because for now we can only ask atomic queries about the data that they are obtained from. So to be able to do this, the model includes multi-layer perceptrons for both relations between individuals and class memberships of, so for single individuals. And this second step is only uncovering knowledge that was already encoded during the learning process. And the idea then is to be able to unravel these complex relationships and be able to consider both relations and classes simultaneously, like ontological reasoning does. And one of the clarifications that the authors make explicitly in the paper is that triples are not treated as text. It's not like you're learning from a textual description of the database. So RRNs are agnostic to the individual names. So they're trying to learn the relationship that they have, that the individuals have among each other in the database, and how to encode the possible inferences that you can make, but it's not important what they're called. So a few assumptions, like we mentioned before, and that the authors also make explicitly, is that we have a fixed vocabulary, so everything but the data, including the individuals, will be fixed. Relations are either unary or binary, and databases can be seen as sets of triples. So relationship R involving individuals I and J is simply I relation R and J, and a class membership is simply, we have like a member of specific, like a reserved relation where I is member of C. And negated facts are just simply encoded with different relation symbols. Here, the authors use the connective, the negation connective for the name. So this is why I use the quotes here. So not R would be the relation name. Maybe it would have been better to, instead of use the connective, say something like not, and NOTR, and the same for member of. And for every knowledge base, we'll have an indicator function that simply maps individuals to vectors. And this will give us 1 if in the position for the member of, or the not member of, and 0 otherwise. So -1 is for negation, 0 is for I don't know, and 1 is for membership. And as is usually done in machine learning approaches, the vectors will just summarize all the information about the individual's class membership given explicitly in the facts. And the trained model will then be of the form, we'll have a probability distribution over what is true in given this this ontology, right? So where T here is an arbitrary query. You want to know if something holds, that will be a triple, and you'll get a probability distribution like it says here on the right-hand side that expresses the model's belief regarding the truth of the query. And managing, having probability distributions will allow for training using cross-entropy error. And the authors point out that during evaluations, they set a 50% threshold for queries to be predicted to be true or false. So if it's 50% or more, it'll be true, otherwise it'll be false. Another thing that the authors go out of their way to specify is that they use the term truth specifically because so instead of saying this, instead of saying I want to know if this is true, if this holds, the relation holds, the entailment relation holds, since the neural network will provide a prediction even if the query is not provably entailed by the ontology. So it could, as we'll see with some extra experiments that the authors do to see how robust to noise the model is, sometimes the neural network will be able to provide a thumbs up for a specific query that the ontology wouldn't be able to do under the cases, the situation, for instance, of noisy data. Another interesting aspect is that training can be done using an actual database, or if you only have rules, as one of the data sets that the authors use in the evaluation, if you only have rules, you can generate a database based on those rules, generate a bunch of those, and use those as training data.
Another question.
Oh, yeah?
Yeah, so just from my understanding again, so the RRN will, you pass it a triple, it'll grab like the embeddings, and then it will pass those embeddings to an MLP, which will then output, like a softmax for like true or false, right?
Right.
So I'm wondering, where does this become like a recurrent neural net? Because, right, like in recurrent neural nets, like the output of time 1 or of time t-1 is also the input at time t. So I guess I didn't see that like come into play.
That's coming right up. Well, we'll see specifically how that comes into play in just a second. So right here in these update layers is where it's going to happen. So just to finish the setup, the model will then have individuals represented as unit vectors in real space, D-dimensional real space, and D here is a hyperparameter, so we have to decide how many dimensions you want to make use of for these embeddings. And the authors point out that it has to be based on the ontology, based on things like expressiveness, vocabulary size, and number of individuals. So this is a very important part to get right. And we'll have update layers that we'll see in just a second that will have to define two kinds, one for relations and another for classes. Since relations are in general not symmetric, you can assume that if I and J are in a relation, then the dual will hold, so Ji will also hold. We'll have in total 4 update layers, so for subject and object, and for positive and negative. And this is where the recursive aspect comes in. So they'll define a gated network, which is just kind of, like I was saying before, a kind of RNN, where gates control how candidate update steps are applied. So a very brief refresher on what gated recurrent units are that the authors base their setup on. Simply like the person asking the question just now was saying, we have these update or forget gates, update gates in the GRU terminology. They will control how much of the new candidate is being incorporated, and so it's very complicated to go through this intuitively, actually, but this is simply doing this aspect of the networks that are taking, they're doing passes based on previous inputs, so that they can essentially encode some kind of context. So a lot of the intuitive explanations of these networks that I've seen typically use text, because I think that's what they were developed especially for, where they say, if I have a long sentence and I want to get right what the next output should be. If I'm generating text, for instance, then if I say, for instance, the tea in the cup, which was blah 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 blah, and then I continue talking about the tea, is hot, for instance. That hot refers to the tea, and in order to be able to keep this context, we have to be able to have this kind of structure, right? So in this case, yeah.
Hi. Yeah, you mentioned that due to the recurrent, the paper uses a recurrent neural network like a GRU due to the fact that the text, you need to keep the context if you have a long sentence. But is there any reason why the work specifically used a GRU compared to, let's just say, an LSTM that is also a gated recurrent neural network and might probably be more apt for longer sentences, or was it empirically already shown that a GRU was much more better for this context?
That's a good question, actually, but the authors don't give any explanation in the paper that I was aware of. They just said, well, we need, actually, thanks for the question, because I talked about the text, but I didn't realize that I didn't say that the important thing is that the authors are doing it so they can keep track of the inferences being carried out in the ontology. So they're not dealing with text, they're dealing with inferences, right? So it's the same kind of thing. You need to keep track of what's going on in the inference so you get right the encoding of the rule. They don't, to my knowledge, differentiate between vanilla LSTMs and like neural networks based on GRUs. They just said, we'll do it this way. I presume that they tried out different kinds, and these were the kinds that worked better. Maybe it's buried in an appendix and I didn't see it, but that's a good question.
Another question.
I'm kind of like just along the lines of what he was asking. Like generally speaking, a GRU is like more efficient than an LSTM. So it's just it's like basically a GRU is just a simplified LSTM.
Yes.
In the paper, they cite another paper on like differentiable computing. And so there's a few different sequence models they can choose from. If you like dig around in the references, it's probably fine answering that.
That makes sense on the efficiency because I think, yeah, the LSTM.
It just has like a few fewer like elements in its hidden state, but otherwise it's just an LSTM that's simplified.
Yes.
So in practice, it's more efficient and can learn just about the same things.
Cool. Thank you.
Great, thanks for the clarification. All right, so the way this is mapped in this is back to the paper, then we have then a gate controlling how much of the update is applied. Here we have this notation here referring to so moving like an arrow pointing to the left for the predicate, it's updating the subject's embedding, and they have one for the object, which is also analogous. So here we have the subject and the object, and P is the predicate. Sigma is just a logistic function, and here is where the calculation of the candidate update steps are carried out. And all of these are the model parameters, right? And then we have a simultaneous update operation where we update based on this triple, and we do, both sides of the update. This is for the one-sided updates for relation. So for relation, so one-sided and then the simultaneous update. For classes, we have the same kind of thing. So classes are much simpler because they're one-sided. We don't have two individuals participating, and we don't even need a positive and negative version. We can just train one and then take the one minus to refer to the negation. So in this case, the model parameters are just these two vectors. And the algorithm, as I mentioned before, for doing this is not involved. So this is a quick overview of this. You can optionally have a matrix of initial embeddings. If they don't, you just randomly initialize. And simply for n iteration, which is also a parameter of the algorithm, you just do this update based on the triples. So for each of the individuals in the KB and each of the triples for the relations, you just do this update step and then you're done. So this is where we can see materialize what we said in the intuitive part, where we had to go through all the data multiple times. So for prediction, this is where the MLPs come in for computing the prediction. So we have a single MLP, multi-layer perceptron for all of the classes. It's called MLP classes. And this MLP will just take a single embedding as an input and return the probabilities for the corresponding individual's membership in all of the classes, right? So for each of the classes, I'll have a probability. And then one for each relation, also in the vocabulary, MLP-R, that will take, in this case, a pair of embeddings and provide a probability for the relation to hold between these two individuals. And the negation is just computed, as I said before, also one minus this output. So training also, not really much to say, is done, as I mentioned in the intuitive part, via samples of databases, which are sets of facts, as we call. that are associated with an ontology. This is the interesting aspect that Paulo was also mentioning before. So you have your training data can be considered to be a manifestation of the rules that they must obey. Okay, so only the DBs are used, not the rules in the training process. And this, I also briefly mentioned this, if you don't have any data, you can just use the rules to sample, to generate DBs for training. And this, the authors go into a pretty long discussion saying why this is a great idea, because it allows for a balanced use of all the rules that might not happen in a real database. And training can also be done on facts that only appear as inferences and not as facts in the database. That can happen perfectly. So, for instance, with our very simple ontology, you could have, all of your artists encoded with their specific trades, right? So you had the sculptor, you had the painter, and maybe Michelangelo was never referred to as an artist in the data. So in this case, if you apply the rule that all painters are artists, then that data will be more representative of the inferences that can be performed with the ontology.
Real question.
Yeah.
So, since you have the rules and you're generating databases for training, so can we consider this as an unsupervised learning or semi-supervised learning paradigm? Because in those learning paradigms, we generally generate the data set rather than directly having labels and classifying.
I hadn't thought of that, but I think it's still supervised because you're generating the data and labeling it as okay because I know that it's true, right? It's I apply the rules and then just get rid of the rules, but the data, I'm not making anything up. I'm just applying the inference engine.
So more like active machine learning kind of thing.
Maybe I hadn't thought about that, but yeah. So then, even though a single training example is considered at a time, because but samples are complete databases. So the authors also point out that this corresponds to training with mini batches. And the procedure itself, as I mentioned a couple of times, is straightforward, and the overview is simply this high-level algorithm where you keep going while the evaluation error has not converged, and for each database in the training samples that you have, you generate the embedding matrix, you compute the loss, both from facts and inferences, update the model parameters to minimize the loss, and keep going. Right. So the training, there's nothing new here in the training process.